Hello, in this course, I will explain how to do homework 1 in the basic electrical engineering course or the EES203. So let's get started with the first question. Find the charge that has entered the terminal from the element from t equals 1 second to t equals 3 seconds when the current entering the element is as shown by the following figure. So we've been given the graph, so let's look at its axis first. In the x-axis, it's time with the unit as second, and the y-axis as current with the unit in amperes. So firstly, we should know the formula for finding the charge, which is given in the lecture note as Q is equals to the integral of the current with respect to time. Therefore, we have to find the integral, or we can just find the area under the graph. So in this case, we want to find the charge that has entered from t equals 1 second to t equals 3 seconds. So that would lead to finding the area under the graph for this section. And if you look carefully, the shape is a trapezium, which you should have learned in high school that the formula for the trapezium is a plus b divided by 2 multiplied by the height. So let's look carefully at what the numbers are. So A and B is the values here. So in this case, this would be 1. And for the value of B, it would be here, which is from 0 to 3. So that would be 3. And the height would be the value here, which is 3 minus 1. That gives us 2. So if we plug it into the formula, we can get 1 plus 3 divided by 2 multiplied by 2. That would give us to 4. And then don't forget the units. Since the unit here is standard and there's no prefix in front, we can just write C here. That would give us the answer for the first question. For question 1.2, the prefix of tera stands for. So we can look in the table given to us in the lecture, and tera would be here, which has a symbol of the capital T and has the multiplier of 10 to the power of 12. So the answer would be 10 to the power of 12. Let's move on to question 1.3. A Walker's cassette tape player used 4 AA batteries in series to provide 6 volts to the player's circuit. The 4 alkaline battery cell stores a total of 200 watt-seconds of energy. If the cassette player is drawing a constant 10 milliamps from the battery pack, how long would the cassette operate at normal power? So the question is asking for how long, which is asking for the time. And then we've been given 3 details of the volt being 6 and the energy being 200 watt-seconds, or you can say joules, whatever you prefer, and the current as 10 milliamps, and we should convert that into amp, which is 10 to the times 10 to the minus 3 amps, which is equivalent to 0.01 amp. So if we look at the equation in our lecture, we have the value of V, I, and W, and we want to find time. So let's put it all in the equation. So we have 200 over by time equals to 6 times 0.01. And if you rearrange the equation, you would get time is equal to 200 divided by 0.06, which is equivalent to 3.33 times 10 to the power of 3 seconds. And that would be the answer. On to the next question, 1.4. Prove that if a circuit has n conductors, G1, G2, all the way to Gn, in parallel with the source current I, the nth conductor, Gn, would have the current of In equals to Gn over Geq multiplied by I. So we want to find the current for the nth conductor, where we've been given that Geq is the sum of all the other G's. So G is the unit of the conductance, which is the reciprocal of the resistor. And from the equation V equals IR, if we substitute R into this, we would get V is equal to I over G. Or if we rearrange it, G is equal to I over V. Now, from the given equation, Geq is equal to G1 plus G2 plus all the way to Gn. If we substitute this equation into each individual G's, we would get Geq is equal to I1 over V plus I2 over V plus In over V. The reason why the V are the same is because the elements are connected in parallel, and in parallel the voltage across the element is equal, but the current isn't. So we can multiply both sides by V. That would eliminate all of these, which would give us V times Geq is equals to I1 plus I2 all the way to In. And in parallel, we can say that the source current I is equal to the I separated in parallel. So we can summarize all this into I. That would give us V times Geq equals I. Now, we can use this V up here that we've found by substituting R inside. And then we want to find the V from the nth conductor. So we would sub in the N into both of this. So that would give us In over Gn multiplied by Geq equals I. And now it's very similar to the final product that we need. So let's rearrange that, and that would give us In is equals to Gn over Geq multiplied by I. And that is the final answer. On to question 2. Basic laws. Find RAB in the following network. So we want to find the total resistance of the circuit between A and B. So if you look carefully, we can ignore anything in the middle because these are the same node. There are no elements blocking the way, so therefore it can short circuit, and that would give us the value of 0 ohms. Next, 2.2. Determine the values of the resistance R1 and R2 for the following circuit. So we have to find the resistance of this and this. So how should we start? If you don't know where to start, you should find the value of every element, like the voltage, current, and the resistance of every element. So let's find the voltage of every element first, since we have the voltage here already and the voltage here, and both of these are equivalent. So we can compress the parallel circuits together. That would give us the new circuit of 24 volts. This is R1. This is 40 ohms parallel with R2, which we don't know the answer yet. And this is 8 volts. And we can say that this is Vx. So using Kirchhoff's voltage law, we know that the voltage around the loop is 0, KVL. So if we look clockwise direction, let's start from here. We go up here, it enters from the negative node, so that would give us minus 24. And then following through, we enter here through the positive, that's 8 plus 8. And then follow through, we enter this element at the positive node, and then we can do plus Vx equals 0, since we loop back to where we start. So basic math, we rearrange plus minus, we get Vx is equals to 16 volts. So we now know that the voltage across this resistor is 16 volts and the voltage around this resistor is 16 volts. Next, we have the knowledge of the 1.6 amps here. So let's find the current through both of this, where let's name this I1 and this is I2. So through Kirchhoff's current law, we know that the current of I going in a node should be equals to the current of I going out. So looking at this node, we can see that I1 is entering and we have I2 and 1.6 amps leaving. So setting up the equation, that would get I1 equals to I2 plus 1.6. And then since we know that the voltage here is 16 volts, we can find the current passing through this resistor using the formula V equals IR. I equals V over R. We can use that to find this I2. So that gets us 16 over 40 plus 1.6. That would give us 0.4 plus 1.6, which is equals to 2 amps. So now we know that the current passing through I1 is 2 amps. So let's just do simple. V equals IR again. R is equals to V over I. And that gives us 8 over 2, which is 4 ohms. 8 from the value here and 2 from the value we calculated. And for I2, we can do the same thing. V over R is equals to 16 from the value we calculated from Vx over 1.6, what we've been given. That would give us 10 ohms. So the final answer would be R1 equals 4 ohms and R2 equals 10 ohms. On to question 2.3. What value of R in the following circuit would cause the current source to deliver 800 milliwatts to the resistor? So we want to find the value of R, and we know that it delivers 800 milliwatts to resistor. So first of all, we have to combine the resistors into one element for easy viewing. And you can see that you cannot add them up in series, or you can parallel them because there's elements stuck in between. For example, this one. So in this case, you would need to use the transformation, either the delta to y transformation or y to delta transformation. In this case, if you look carefully, this is the same node and this is the same node. So you can see that it's the delta triangle here or the delta triangle here. So let's just pick one. I'm picking the bottom one. And if you transform it, it would look similar to this Y formation, right? And the formula for converting delta to Y is given in the lecture as the product of the two sides divided by the sum of all the resistors. Since every resistor is exactly the same, we can do R1 equals to R2 equals to R3, since the result would be equal. And then if we calculate it, it would be R multiplied by R over R plus R plus R, which would give us R squared over 3R. And cancel the R out, it would get R over 3. So that means that this small resistor is R over 3. Now let's redraw the circuit. We have the current source of 30 milliamps going up, and then the resistor with the Y formation, and this is R, this is R over 3, R over 3, R over 3. Alright. Now you can see that it's possible to calculate this with series or and parallel. So you can see that these two are in series and these two are in series. That would give us R plus R over 3, which would give us 4R over 3. And since these two share the same node, as the node being this part and this part, we can parallel these two together. So let's 4R over 3 parallel with 4R over 3. Let's quickly calculate that using the product between them times divided by the sum, which is 16R squared over 9 divided by 8R over 3, which would give us 2R over 3. Now, for a quick hint, in the delta to Y or Y to delta, if the resistor is equivalent, we can just divide it by 3. So, for example, in this one, every resistor has the resistance of R, we can just divide by 3. And when you parallel the same amount of resistance, you can just divide by 2 without having to do this calculation. For example, this is the same, right? So we can divide this by 2. That would give us 2R over 3, which is equal to 2R over 3 here. Now, you got the parallel resistor of 2R over 3 here. Since this hasn't been calculated yet, and we calculated 2R over 3 here. And let's series these two together. That would give us 2R over 3 plus R over 3, which would give us R. Meaning that this whole resistance here has the value of R. And now it wants to find us the value of R when we deliver 800 milliwatts. So we've been given P is equals to 800 milliwatts, which is equals to 800 times 10 to the minus 3 watts, or 0.8 watts. And we've also been given I equals 30 milliamps, or 30 times 10 to the minus 3 amps, or 0.03. And now we know the equation of P equals to IV, and we don't have V, so we can use the Ohm's law of V equals IR and substitute V inside. That would give us P equals I squared R. Now we have everything. Since we have P and we have I, we are looking for R. So let's put everything into the equation. 0.8 equals 0.03 squared times R. That would give us R is equals to 0.8 divided by 0.03 squared, which would give us 8.88 times 10 to the minus 2 ohms. That would be the final answer. Now on to question 3, method of analysis. 3.1, find VC by using nodal analysis. So we want to find the voltage of this node here, VC. So let's look at how to solve nodal analysis first. Here. So determine number of nodes, select reference node, assign variables, and use KCL, and then solve. So let's look first. Since this has voltage source, let's look at the cases. There's two voltage source here, so let's look at which case is what. So case 1, if a voltage source is connected between the non-reference node and a reference node, in this case, we have the reference node as the bottom here, VG equals 0 volts here. Since this voltage source is connected to a reference node and a non-reference node, we can say that the voltage at the non-reference node is equal to the voltage of the voltage source. That means that we can determine the voltage at this node, VB, is equals to minus 12 volts. The minus comes from the sign here, where this positive sign is heading towards the 0 volts. That means that 0 minus 12 volts here equals to minus 12. And for case 2, if the voltage source is connected between two non-reference nodes, we call it a supernode. That means that this voltage source here is connected between VA and VC, which we don't know the value of. So that means that this is a supernode. And then when we have a supernode, we can do the KCL and KVL apply to it. So we treat it as a single node here. So let's look at the KVL at the supernode first. The KVL, a quick way of determining this is just looking at the sign of the voltage source. Since the positive here is connected to the VA here, we can assume positive sign to VA. And then the negative sign here is connected to the VC, so we can just do minus VC. And that would be equal to the voltage of the voltage source, which is 10 here. And then we can rearrange it. VA equals to VC plus 10. And that would be our first equation. And now we can do KCL at supernode. So KCL, or Kirchhoff's current law, states that the current in going into a node should be equal to the current out leaving the node. Since we treat that this is a same node, we can determine what current goes in and out of it. So let's assign current variables first. So let's say that is I1, and this is I2, and then we can find the current going into this yellow node here, which is 5 amps here, and I2 here. So we can do 5 plus I2 equals to the current leaving the node. So this yellow part, what is leaving? We can see that 2 is leaving and I1 is leaving. So let's do I1 plus 2. And now we can use Ohm's law, saying that V equals IR. And that right now we have R, so let's rearrange it to I equals V over R. And V is basically the voltage difference between two nodes here. So let's do 3 here if we move 2 to the side, and then we can substitute this equation into each individual i's. So let's do I2 first. I2 is this side here, where we have VB in the beginning and VC in the destination. So we do VB minus VC over by the resistor 40 ohms would be equal to I1, which is this part here where it's VA minus VB divided by the resistance is 10 ohms. And now we can substitute VB inside since we already found it in the beginning here, minus 12. So let's do 3 plus minus 12 minus VC over 40 equals to VA minus 12 is plus 12 over 10. And now let's multiply everything by 40. That would give us 120 minus 12 minus VC equals to 4VA plus 48. And now let's rearrange that. Let's move VC this side and 48 this side. That would give us 120 minus 60, that is 60, equals to 4VA plus VC. And that would be our second equation. And if we have our first equation here, VA, we can substitute VA inside the second equation. So let's do first equation into second equation. That would give us 60 equals 4 times VC plus 10 plus VC, right? Then expand this out, and then we would get 60 minus 40, that would be 20, equals to 4VC plus VC, that's 5VC. And then 20 divided by 5, VC would be 4 volts. And that would be the final answer. On to the last question, 3.2. Consider the following circuit where R1 equals R2 equals 1 ohm and R3 equals 2 ohm. Obtain the mesh current equations for the circuit in matrix form. So let's look at how to solve this using mesh analysis. So let's look at the cases first. We can see that there's two current source here. So let's look at which one is what. Case 1. If a current source exists only in one mesh. Here, let's look at this one. This current source exists in between mesh 2 and mesh 3. So we can't say that. But if we look at this one here, it only exists in one mesh. So we can say that the current of the mesh is equal to the current of the current source. So the current of this entire mesh would be equal to 4 amps. So we can say that's our first equation. I1 equals to 4 amps. Now let's look on the second case. If a current source exists between two meshes, like this one, it's called a super mesh. And then we can apply KCL and KVL to determine the mesh currents. So let's apply the KVL first. KCL, I apologize, at the super mesh. As you can tell, KCL is current in equals to current out. And if you look at this node here, if you look to the left first, I2 travels in the clockwise direction, so it leads here, and it enters the same way as the current source. So that would be the positive side, that would be I2 here. On the other hand, you can see that I3 here goes clockwise, but it enters from the bottom of the current source, so that would give us minus I3, and then equals to the current source 5 here. And this is our second equation. And now let's do KVL at the super mesh. And now, since this is a super mesh, we can treat this as one mesh here. We can ignore this. So we would calculate the KVL, which is the voltage around a loop, has to be equals to 0 here. So let's do KVL around this part. So let's start here first. If we move up here, we can see that it enters from the negative node. So that would give us minus 10 here, as the voltage around the loop is 0. And now following through, we would enter R1 here first. And since R1 here is in the same direction as R2, but the opposite as of I1, we can say that it's equals to plus 1 times I2 minus I1. How we get this equation is from the Ohm's law V equals IR, where the R here is 1 and the I here is I2 minus I1 since it's conflicting. And now carrying on here, we hit R2 here, and then R2 is also 1 ohms given here, and we have I3 traveling in the same direction and I1 traveling in the opposite direction. So that would give us plus 1 times I3 minus I1 equals plus, and then carrying on, we have R3 here, which is 2 ohms, and then it only has one current, which is I3. So that would be plus 2 I3 equals to 0. And now we already have we can simplify this and put it into the matrix form, or we can simplify it a bit using I1 here. We can substitute I1 equals to 4 into I1 here. So that would give us minus 10 plus I2 minus 4 plus I3 minus 4 plus 2I3 equals to 0. So we simplify that a bit, we would get I2 plus 3 I3 equals to 18. And that would be our final third equation. And now to put it into matrix form, we can just do the simple format of how many i's we have. So we have three unknowns. That would be I1, I2, and I3. So from the first equation here, I1 equals to 4. Since we have 1 of I1, we will do 1 and none of I2 and I3. That would be equals to 4. Since in matrix we multiply this by this, plus this and this, plus this and this will be equals to 4. And on to the second equation, we have no I1, so that would be 0 here. And I2 is 1, and I3 is minus 1, which was 5 here. And now finally, the bottom last equation. I2 is 1, I1 is 0, and I3 is 3, which is 18 here. So this would be the final equation. Note that in matrix form, there can be multiple answers, but it should be equivalent when simplified.